Hi everybody, this is Jake Spencer, and today we're going to be looking at section 3.6, Balanced Equation Stoichiometry Equations. So when we have balanced equations, we can actually determine a lot of quantitative information. So a big thing about this chapter that it's important to keep in mind is that the coefficients in a balanced chemical equation represent the relative number of molecules in a reaction. So when we have the balanced equation of water here, which is 2H2 plus O2 is 2H2O, that means that 2 molecules of hydrogen gas plus 1 molecule of oxygen gas is going to equal 2 molecules of water. And that ratio is always going to be consistent. That is the relative number of molecules in the reaction. Not only do the coefficients indicate the relative number of molecules, or FUs, but they also represent the relative number of moles in the reaction. So we have the 2 molecules plus 1 molecule equals 2 molecules, but that also means that 2 moles of hydrogen plus 1 mole of oxygen gas is going to form 2 moles of water. This is a good visual from the book that really puts the ideas up to this point into display. So we have our balanced chemical equation with the formation of water. When we look at the molecules, it makes sense. Like when you just look at the pictures, we have these 2 molecules of H2O. So this pair bonds with this oxygen, and this pair bonds with this oxygen. And that's why when we add 2 molecules of hydrogen to 1 molecule of oxygen, you're going to get those 2 molecules of water. So I think that's just a good way to display the ideas. Not only that, but we can use the relative number of moles to determine the relative number of grams. So when you have the 2 moles of hydrogen plus the 1 mole of oxygen to make the 2 moles of water, that's the same thing as saying 4 grams of hydrogen gas plus 32 grams of oxygen gas is going to equal 36 grams of water, which, mathematically checks out. 4 plus 32 equals 6. So when our chemical equations are balanced, we create these relationships called stoichiometrically equivalent quantities, which is basically saying that in the formation of H2O, 2 moles of hydrogen gas is stoichiometrically equivalent to 1 mole of oxygen gas, which is equivalent to 2 moles of water. And that's what this symbol means. This symbol right here means that it's stoichiometrically equivalent to. So these 2 moles of hydrogen are equal to these 2 moles of water, and vice versa, because in this reaction, that is always going to be the ratio. So how can we use this stoichiometric relationship to our advantage? We're going to look at our first example here. We're going to stick with the formation of water, and we're going to determine how many moles of water are produced when 1.57 moles of oxygen gas are allowed. So we're going to take our given 1.57 moles of oxygen gas, and we're going to use dimensional analysis to convert those moles of oxygen gas into moles of water, because we know that 1 mole of oxygen gas in this equation is stoichiometrically equivalent to 2 moles of water. So we're just going to multiply 1.57 times 2 because we canceled out those units. We're going to end up with 3.14 moles of water. So when you have 1.57 moles of oxygen gas, you're going to produce 3.14 moles of water in this particular equation. For our next example, we're going to go a little more in depth, and we're going to take a look at the combustion of butane. This is a combustion reaction, and it's a little more complex because we have 2 different products from 2 different reactants. And the coefficients are obviously a lot bigger and a lot different. So the ratios are going to be different. So just always remember that these coefficients in this equation are going to be equivalent to each other. So 2 molecules of butane plus 13 molecules of oxygen gas is going to produce 8 moles of carbon dioxide and 10 moles of water. Or 2 moles plus 13 moles is going to produce 8 moles and 10 moles. So let's calculate the mass of carbon dioxide produced when 1 gram of butane is burned. And we can do that with a combination of molar conversions from example 1 and just simple dimensional analysis converting moles to grams with molar mass. So here we have the 3 steps needed to find out how many grams of carbon dioxide are produced from 1 gram combustion of butane. So first we're going to want to convert those grams of butane into moles of butane, which is seen right here. And now that we know how many moles of butane we have, we can use dimensional analysis, and right here is the key. These 2 quantities right here are stoichiometrically equivalent. As we see right here, we got the 8 moles of carbon dioxide from 2 moles of butane, and those are equivalent. So that's why we can cancel out these units, and now we know how many moles of carbon dioxide are produced thanks to that ratio of 2 to 8. Finally, this is a pretty simple dimensional analysis conversion. We're just going to use the molar mass of carbon dioxide, which is 44 grams, and multiply that by the moles of carbon dioxide that we've produced, and that's going to leave us with 3.03 grams of carbon dioxide. So we're going from gram to moles of given, and then converting the moles of given to the moles that we want to find using molar conversion, and then going from moles to grams of our final answer. This is a good graphic organizer of the steps that we just did to go from our given to what we want to find. And this on the bottom is just all the steps from this slide put into one big dimensional analysis equation. Now that we know how many grams are produced of carbon dioxide, how can we determine the grams of oxygen that are consumed? So even though oxygen gas is a reactant in this equation, it's going to be the exact same as finding out the product that is carbon dioxide. The only thing that's different is that we're using a different stoichiometrically equivalent quantities. So we're given the 1 gram of butane. We're going to use the molar mass of butane to find out how many moles of butane we have. And then we're going to use our molar conversion, which is 2 moles of butane to 13 moles of oxygen gas. And then finally, we're going to convert those moles of oxygen gas into grams of oxygen gas using molar mass. And that, in the end, leaves us with 3.59 grams of oxygen gas. Anyways, that is going to be all for today's video. I want to thank you all so much for watching. I hope this comes as helpful to you or useful in any way possible. And best of luck on your exams in May. See ya.